Imagine a hospital chatbot going rogue and providing hallucinatory diagnostic advice because a user actively tricked its safety protocols.
Right. That is a complete nightmare scenario.
Or, picture a major retail bank deploying an automated system that denies hundreds of mortgage applications without being able to mathematically explain a single decision to the auditors.
Yeah, that happens more often than people think.
The stakes for deploying artificial intelligence in the real world have just never been higher. Today, we are dissecting the exact mechanisms developers use to prevent those catastrophic failures. Welcome to the Dupe Dive. Our mission today is highly specific. We are unpacking a source document containing 10 critical practice questions for the AI-901 exam.
And to respect your time and, maximize the technical density of what you walk away with, we are adopting a strict structural format for this deep dive.
Sounds good.
The host will read the core scenario of each practice question directly from our sources. We will strictly skip reading the 4 multiple choice options aloud.
Right. Nobody wants to hear a list of wrong answers.
Exactly. I will then immediately provide the correct answer letter, followed by a concise 1 to 2 sentence explanation of the core concept. After that, we will dissect the underlying architecture to understand the how and the why.
Okay, let's unpack this, starting with our first theme, which is how an AI model physically ingests and translates the messy, unstructured reality of the physical world.
It is very messy out there.
It really is. Here is question 1. A retail company wants customers to upload a photo of a broken appliance part and receive a text description of the likely replacement item. Which model capability is required?
The correct answer is B. Image-to-text capability allows an AI model to analyze the visual details of the broken part and generate a textual description of the replacement item.
So the model isn't just like tagging the photo with predefined labels.
No, not at all.
It's actually generating descriptive language based on an array of pixels. It's like having a digital hardware store clerk looking over your shoulder. But mechanically, how is it bridging that gap between visual light data and human vocabulary?
Well, it relies on a multimodal architecture. The system uses a vision encoder, which is often a convolutional neural network, to break that image down into mathematical representations of shapes, edges, and textures.
Okay, so it turns the picture into math.
Exactly. Those mathematical representations are then mapped into the exact same mathematical space that the language model uses for words.
Wait, so when the model sees the specific geometry of a broken agitator coupling from a washing machine, it mathematically aligns that geometry with the text tokens that describe it.
Yes, it is translating the physical geometry directly into the model's internal vocabulary.
Wow. But a static photo is a relatively clean, controlled input. Corporate environments are rarely that clean. Data usually arrives in a highly chaotic mixture of completely different formats.
Oh, definitely.
Which brings up question 4. You need to extract dynamic structured information from a mixture of unstructured text and audio recordings. Which service is most appropriate?
The correct answer is A. Content understanding is designed to extract structured information from multiple forms of unstructured content, including both text and audio.
This sounds like magic, but I know it's just math. We're talking about normalizing a voicemail, which is just an audio wavelength, and an email, which is text into a single, clean database table.
Right, it normalizes the data streams.
But how does a single service parse both acoustic wavelengths and text characters to find the same underlying information?
Well, the content understanding service doesn't treat the audio as a sound file for very long. It passes the audio through a sophisticated transcription layer first, converting those acoustic frequencies into text tokens.
I see, so everything becomes text.
Exactly. Once both the email and the voicemail are represented as text tokens, the system applies a unified extraction model. It looks for patterns like dates, dollar amounts, or entity names across the entire normalized data set.
Regardless of whether that data originated from a keyboard or a microphone.
Precisely. It forces everything into a common language first.
But that strategy hits a wall if the transcription layer itself doesn't recognize the words being spoken. Like, what happens when the audio contains vocabulary that simply doesn't exist in the standard dictionary?
That is a very common issue in enterprise setups.
Right. Here is question 3. Your application needs to transcribe customer service calls that contain highly specialized, proprietary industry terminology not found in standard dictionaries. Which features should you utilize?
The correct answer is B. Custom vocabulary enables speech recognition systems to accurately recognize specialized industry terms and acronyms that standard language models miss.
This is a massive friction point in enterprise AI. I mean, If an engineer mentions a proprietary internal system like Aegis 7, a standard acoustic model might transcribe that as Aegis 7 or just complete gibberish.
Yeah, it absolutely would.
So how does feeding it a custom vocabulary actually change the model's listening behavior?
It mathematically adjusts the probability weights within the acoustic model. Speech recognition works by guessing the most likely sequence of letters based on the sound waves.
Okay, making an educated guess.
Right. Normally, Aegis 7 has a much higher statistical probability in the English language than Aegis 7.
That makes sense.
By implementing a custom vocabulary, you are manually overriding those baseline probabilities. You are telling the model, hey, if you hear this specific sequence of phonemes, heavily bias your output toward our proprietary acronym.
So it overrides the default guess.
Yes. And if we connect this to the bigger picture, these first few concepts are entirely about perception. We are forcing these systems to accurately ingest the jagged, messy inputs of human communication.
Whether that's a greasy piece of plastic in a photograph or a rambling voicemail.
Right, or a highly technical acronym. If the system cannot perceive the data accurately at the perimeter, any downstream reasoning it does will be inherently flawed.
But perceiving the physical world is only the first step. Once the AI can accurately hear and see the inputs, we have to ensure it actually reasons over factual current data.
Grounding is critical.
Yeah, an AI that perfectly transcribes a user's question but answers it using a 3-year-old database is completely useless. How do we keep its memory perfectly fresh? Let's look at question 2.
Go ahead.
To prevent a generative AI model from providing outdated information, you decide to implement a retrieval-augmented generation pattern. What is the primary role of the generative model in this specific pattern?
The correct answer is D. In a retrieval-augmented generation pattern, the generative model uses the newly retrieved grounding data to formulate a natural language response, rather than permanently storing the data or retraining itself.
So this separates the brain's ability to speak from the brain's storage of facts. It's essentially an open book test for the AI rather than relying on its memory.
That is a perfect analogy.
Instead of forcing the model to memorize the company handbook during its initial training, the retrieval augmented generation pattern, or RAG-RA, forces the model to act as a synthesizer. You retrieve a fresh document, shove it into the model's context window, and tell it to only synthesize an answer from that specific document.
Precisely. The generative model is restricted to processing the text provided in the prompt at runtime. It completely eliminates the reliance on the model's static, pre-trained weights for factual recall.
But if the generative model is just the synthesizer, what is actually doing the heavy lifting of finding that specific document in the first place?
That is where the retrieval part of RAG comes in.
Right, so if an employee asks a question, how does the system physically pull the right file from a massive corporate server? Here is question 8. You are configuring a single-agent solution in Microsoft Foundry that needs to answer questions based on a company's internal, frequently updated knowledge base. Which capability should you integrate?
The correct answer is C. Enterprise Search allows an AI agent to access and retrieve current organizational records from an internal knowledge base instead of relying on pre-trained knowledge.
So Enterprise Search is the actual API mechanism. It's the secure pipeline that indexes all those PDFs, Word documents, and intranet pages and makes them available to the AI agent.
Yes, it handles the actual retrieval.
But search itself is notoriously brittle. I mean, if I type vacation policy into a legacy search bar and the actual HR document is titled Paid Time Off Regulations, a traditional keyword search completely fails because it's only looking for exact character matches.
Exactly, which is extremely frustrating for users.
How does the architecture solve the problem of human intent? Here's question 9. To improve the relevance of retrieved documents, you transition from exact keyword matching to a method that understands the contextual meaning of the user's query. Which technology should you implement?
The correct answer is C. Vector embeddings represent text as numerical vectors, allowing the system to retrieve documents based on semantic meaning and contextual relationships rather than exact keyword matches.
Okay, vector embeddings.
Yeah, what's fascinating here is we're moving away from traditional Control-F exact keyword searches to systems that actually grasp the intent of what you are looking for. It is the sheer elegance of the underlying mathematics.
How so?
Vector embeddings translate human language into coordinate geometry. Imagine a multi-dimensional map with thousands of axes. The system assigns a massive string of numbers to a chunk of text, plotting it as a specific point in that space.
Okay, I am picturing a giant 3D graph.
Right. Concepts that are semantically related, like vacation and time off, are plotted physically close to one another on that mathematical map.
Oh, I see.
When you query the system, it doesn't look for matching letters. It calculates the cosine similarity. It measures the mathematical distance between your question and the documents in the database, returning the files that are closest in meaning.
That completely eliminates the control F limitation. The system retrieves documents based on the spatial proximity of concepts.
Exactly.
So at this stage in our architecture, we have an AI that perfectly transcribes multimodal inputs, retrieves the most current internal documents based on semantic geometry, and synthesizes an accurate answer.
Which is incredibly powerful.
But in a high-stakes environment like a medical compliance application, accuracy isn't enough. We need total predictability. We cannot have a model that decides to get creative with how it phrases medical regulations.
No, you absolutely cannot.
How do we force mathematical consistency?
Yeah.
Here is question 5. You want your generative AI model to produce highly deterministic and consistent responses for a factual medical compliance chatbot. Which configuration adjustment is most appropriate?
The correct answer is A. Minimizing the temperature setting makes outputs more deterministic, focused, and consistent, which is crucial for reliability in compliance scenarios.
Let's visualize the actual mechanics of temperature. An LLM operates by generating a probability distribution for what the next word should be. I like to imagine a Plinko board.
Okay, a Plinko board.
Yeah, if the temperature is high, the pegs on the Plinko board are spaced widely apart, meaning the next generated word has a higher probability of bouncing into unexpected, less likely slots.
Right, a high-temperature AI is like a jazz musician improvising wildly.
Exactly. This creates varied, highly creative text. But for a medical compliance bot, you want to eliminate that randomness entirely. A low-temperature AI is a classical musician, strictly reading sheet music.
That is a great way to think about it. Minimizing the temperature mathematically alters the softmax function within the model's output layer. It heavily skews the probability distribution toward the absolute highest scoring token.
So you remove the bounce from the Plinko board, the chip falls straight down the middle every time.
Yes. When you set the temperature near 0, you are essentially forcing the model to take the argmax, the single most mathematically probable next word, every single time, resulting in rigid, highly deterministic outputs.
But adjusting the temperature only controls the model's internal statistical randomness. What if a user actively tries to mess with the model? Like, what if they aggressively try to force the model to break character?
That is a very real threat.
Here is question 7. The model occasionally ignores the personality constraints set by the developer when a user sends a highly aggressive message. What is the most robust architectural approach to enforce the desired personality?
The correct answer is D. Strengthening the instructions within the system message is the most robust approach because the system message has the highest priority in guiding behavior and restrictions.
The system message isn't just a friendly suggestion. It operates at a fundamental level in the model's attention mechanism.
It really does.
It's the foundational directive injected into the context window before the user even types a single word. How does the architecture physically prioritize that system message over a highly aggressive user prompt?
It comes down to token hierarchy. During the processing phase, the attention layers in the transformer model are weighted to heavily prioritize the structural constraints defined in the system prompt block.
Okay, so it weighs the system rules heavier than the user input.
Exactly. Even if the user prompt block contains aggressive commands or contradictory instructions, the model evaluates the semantic weight of the system message as the overriding governance layer.
You are establishing a permanent architectural boundary that the user's input cannot easily overwrite.
Yes, that is the goal.
But users constantly invent new ways to bypass those boundaries. They don't just use aggression, they use highly sophisticated trickery.
Prompt injections are getting very creative.
They use complex hypothetical scenarios, or ask the model to translate malicious code into a different language to bypass text filters. How does the developer secure the perimeter against attacks designed to confuse the model's reasoning? Let's read question 6.
All right.
Users are finding creative ways to trick the model into producing restricted content by using complex hypothetical scenarios. What is the most effective native foundry mechanism to mitigate this?
The correct answer is A. Advanced content safety filters are specifically designed to detect and block attempts to bypass restrictions through prompt injection or adversarial prompts.
A system message relies on the language model itself to follow the rules. But a prompt injection attack specifically aims to break the language model's reasoning.
Right, which means the defense has to exist outside of the model entirely.
Oh, that makes sense.
That is the exact architectural shift.
Yeah.
Advanced content safety filters act as an independent pre-computation layer. When a user submits a prompt, it doesn't go straight to the generative model.
Where does it go?
It first passes through these safety filters, which utilize entirely separate, specialized classification models trained specifically to detect adversarial intent vectors and injection patterns.
So if the filter calculates a high probability of malicious intent, it terminates the request at the perimeter. The generative model never even sees the prompt.
Exactly. It is a totally independent firewall intercepting the traffic.
Which brings us to our final question and the ultimate requirement for deploying these sophisticated architectures into real-world, high-stakes environments.
This is a big one.
Here is question 10. When developing a financial loan approval model, you implement a feature that allows users to see exactly which financial factors influence the model's decision. Which responsible AI principle does this address?
The correct answer is B. Providing visibility into the factors that influence a loan decision improves explainability, directly addressing the principle of transparency.
I imagine that is crucial for regulatory compliance.
This raises an important question regarding feature attribution. In complex neural networks, outputs are often treated as a black box. But when dealing with financial loans or medical approvals, regulatory bodies require mathematical proof of how a conclusion was reached.
Right, you can't just say the AI said so.
No, you really can't. Transparency in this context means implementing tools like SHAP values, Shackley additive explanations, which calculate and display the exact percentage of influence each variable had on the final model output.
Variables like debt-to-income ratio or credit history length?
Exactly. You are mathematically proving the absence of hidden arbitrary correlations. As AI takes on high-stakes tasks, proving why it makes a decision is just as important as the decision itself. And as a final thought for you to mull over, we just spent this entire deep dive exploring the intricate architectural mechanisms developers use to force these systems to be predictable, transparent, and grounded.
But there's a human element.
Absolutely. As these tools integrate into daily life, as these models become deeply embedded in the software processing your personal healthcare records, your mortgage applications, and your employment data, how much algorithmic transparency will you demand from the AI systems making decisions about your own data? The technical mechanisms exist today, but it is ultimately the market and the users who will dictate whether those mechanisms are turned on by default.
An incredibly vital question. Keep questioning, keep exploring. Catch you next time.